Okay, today's lesson is on improper integrals. What we're going to do is we're going to spend today on the integral types here on the left side. So these are the ones we're going to look at today. Tomorrow we're going to look at the other types over here on the right side. So we're going to focus on this. Let's talk about what an improper integral is. On the ones that we're working on today, it's pretty obvious that it's improper because it's either going to have positive infinity or negative infinity or both on the integral sign. So it's pretty obvious what they are. Like this right here. So it's either going to go from some number to infinity or from negative infinity to some number, or it could go from negative infinity to infinity. So that's what they appear like. What we do is we actually, when we have one of these, we have to rewrite them using these definitions right here. We have to rewrite them as a combination of a limit and an integral. And so we have two options when we solve one of these. They will either converge, and that means they will basically, the answer is going to be whatever the value of the limit is, 2 or whatever it is. They either converge to a number, or they diverge. You know, maybe they're headed to infinity or negative infinity, and they don't head to any particular real number. And that's what we're going to be looking at today. So let's look at these two formulas, how these formulas work. If I have the integral where I'm going from some number to positive infinity, what I do is I rewrite it. I'm going to take the positive infinity off of the integral symbol, and I'm going to basically put it in the limit. So we're going to go limit from, and A and B are the typical letters that they use. You could certainly use whatever letter you want. That's just typical. They would use B for the upper bound and A for the lower bound. So we would do the limit as B goes to positive infinity of the integral from A to B of f of x. So that's a rewrite. We rewrite it, and then we deal with this kind of like a combination problem. It's both an integral and a limit. If the lower bound is negative infinity, we do the same kind of procedure. We take that off and put an A. We do the limit as A goes to negative infinity from A to B of the function, and we solve that. If we go from negative infinity to infinity, we actually have to split the integral into two pieces. We have to pick some number that we're going to go to. I recommend 0. I kind of like 0. So we go from negative infinity to 0, and then we add, from 0 to infinity. This one we would rewrite like this type, and this one we would rewrite like that. So you would really actually have two integrals to do, two combo limit integrals to do for that kind. Okay? And that's what we're going to be working on today. Tomorrow's lesson has to deal with these particular formulas, and it's not as apparent that they're improper integrals. They require a little bit more investigation. So we'll do that tomorrow. Questions so far? Okay. Here's our first example. Let's go ahead and start that one. We see that it's improper. We're going to use our definition to rewrite it. So we're going to turn this into limit as b goes to infinity of the integral of 1 to b of 1 over x dx. So my first task is simply using the formula, using the definition to rewrite it. Okay. Then we would work the integral. Now I'm going to focus my attention on the integral, and I'm going to work the integral, and then I'm going to apply the limit. That's the order that we work it in. So we're going to pay attention to the integral. The limit's just going to kind of come along with it, just hang along, and then we will apply the limit. So limit as b goes to infinity. We know that the integral of 1 over x is ln absolute value x. We will evaluate that from 1 to b. So we have the limit as b goes to infinity. So we substitute our, we do our f of b minus f of a. So I get natural log b minus natural log 1. We know that natural log 1 is 0. And natural log of an ever-increasing number, b is going to infinity, so of an ever-increasing number will make this tend to infinity, which means that it diverges. Our first one, it diverges. It doesn't come out to an actual real number. Okay? So that's our first one. Questions? What I will want you to do is write whether it's tending to infinity or negative infinity, and write diverges. I'm going to want you to do both. Okay? On the AP test, they would typically, if this is a multiple choice question, they would typically write diverge as one of the answers, and then a bunch of numbers perhaps. Yes. Because I'm not headed towards any number. I'm going to infinity. It's not, that means, so these two words right here, diverge and converge, this perhaps is one of the first times we've talked about them. They're quite important as we move into Calculus 2 material. Converge means that we're headed towards a particular number, it's like a limit. The limit is headed towards maybe 3. Diverge means that we are headed to infinity or negative infinity. We are not headed to any particular location. Okay? All right, let's take a look at our next examples. All right. Oh, I need to be able to see this problem. Okay. All right. So the first one on this page, we're basically going to infinity. And so this is similar to the other one that we worked. So let's use that definition. The limit as b, we're just rewriting. Our first step is to rewrite using the definition. Our limit as b approaches infinity of integral of 1 to b of e to the negative x dx. Okay, that's our rewrite. Now we're going to focus on the integral itself. And I encourage you, when we have a negative exponent, go ahead and when you're evaluating, write it as a positive exponent. Then you are less likely to make a mistake, because that's where it gets kind of, there are nuances with the exponent that we need to really pay attention to. So this, actually, the integral of e to the negative x is negative e to the negative x. Okay, limit as b goes to infinity. I'm going to write it as negative 1 over e to the x from 1 to b. Okay? So we evaluate. We get the limit as b goes to infinity of negative 1 over e to the b minus a negative 1 over e to the first. Okay. So on this particular term, as the denominator grows larger and larger, this whole term is going to tend to what? 0. If we left it in negative exponent form, we may have missed it. That's my own reason I'm recommending for you to not leave it in negative exponent form. I mean, you certainly can do whichever one you want, but you might have missed that issue, that it actually is going to tend to 0. That tends to 0. And I'm left with a negative 1 over e, so this particular integral converges to 1 over e. Okay? Let's look at the next one. The next one, we have a negative infinity on the lower bound, so let's rewrite it with that definition. So this is going to be equal to the limit as a approaches negative infinity of a to 0 of e to the, I'm going to write it as 1/4 x. Okay. That's my using the definition. All right, so now let's focus on the integral. Okay, so the integral of e to the 1/4 x, so we have limit a goes to negative infinity. The integral of that is going to be 4e to the 1/4 x evaluated from a to 0. So the limit as a goes to negative infinity. All right, so we're going to place the 0 in. When we put the 0 here in the exponent, that goes to 0. E to the 0 is 1, and 4 times 1 is 4. Okay, minus. So I'm doing my f of b minus f of a. We're going to put the a in, and we get minus e to the 1/4 a. Okay, is everybody okay? All right. Now, this is very significant that we are headed... Oh, yeah. This is very significant that we are going to negative infinity. That's pretty important. Because when I put increasingly more negative numbers, larger negative numbers in here, or technically smaller negative numbers, but as I'm headed to negative infinity, this really turns into 4 over infinity, doesn't it? The negative exponent. It's going to be a negative exponent. So this piece turns into 4 over an increasingly larger number. So what is this term going to tend to? It's going to go to 0. And so basically I'm going to be left with 4. So the exponents play a very important role, and the signs of the exponents play a very important role in this lesson. Okay, our last problem. Here we have, we're given e to the negative x. We are, let R be the region in the first quadrant between the graph of e to the negative x and the x-axis. We're supposed to find the volume of the solid formed generated when R is revolved about the x-axis. All right, let's draw a picture. All right. So e to the negative x starts here at a y value of 1 and then just kind of approaches the x-axis is the asymptote for this guy. Okay. Here's my axis of rotation. I'm going to use discs, and I'm going to measure my R from the axis of rotation to the figure. So my formula, if you will recall, for discs is basically pi r squared. So I have pi. My integral is going to go from my beginning x value, which is 0, and my ending x value, well, really kind of doesn't end, does it? It's infinity, of my function e to the negative x squared. So that's my setup for my integral. Now we can see that that is an improper integral, and we're going to have to use one of our definitions to rewrite it. I'm going to choose to leave the pi outside the limit, outside of everything. I just don't want to really mess with it. I'm just going to leave it right there. So we need to rewrite. This would be the limit as b goes to infinity of the integral of 0 to b. Now this negative x to the 2, I'm going to rewrite that as e to the negative 2x. And that's the integral that we need to work. Okay. So we focus on the integration part, and we take care of the integration part. So the integral of e to the negative 2x would be what? Negative 1/2 e to the negative 2x. So pi limit b goes to infinity. We're going to have, and that negative 1/2 is a constant, so I'm just going to pull it out here. I really don't want to mess with it. I'm just going to pull that out, the negative 1/2, and I'm going to be, so it's negative 1/2 e to the negative 2x evaluated from 0 to b. So that equals negative 1/2 pi, limit b goes to infinity. All right, so let's evaluate that. F of b minus f of a. So we get e to the negative 2b minus e to the 0. Negative 2 times 0 is 0. Okay? All right, so let's think about this term right here. Now I'm not going to rewrite it. I want you to kind of consider this just, in your head. This is a negative exponent, so I think we understand it's in the denominator. And I'm going to put larger and larger numbers down there. So this is going to tend to 0. And I'm going to be left with, I have my negative 1/2 pi times, this is going to be a negative 1. And then I simplify that and I get 1/2 pi is going to be the volume of that solid. Okay? Now before we leave the lesson, I need to take you to your yellow sheet, like page 2. I'm going to pull it up here on the board. Is everybody done with this? Are we okay? Okay. So I need to remind you now. Our limits are really important here, and limits are going to continue to be important. We are not done with limits after like the first unit. I mean, we're not done. Actually, when we get to the series, the power series, we use limits. So limits are with us to stay. And this is one example of requiring use of the limit. So let's refer to, if you have your yellow sheet with you, page 2. We're going to talk about some important limit stuff that maybe we haven't thought about in a while. I know that's hard to believe. But this right here, I think this is page 2. See where it says limits of the ratios of two functions? Make that bigger. All right. Pretty significant when we get to some functions that are difficult to take the limit of, some nuances that we need to think about. So this whole sequence right here, let's first of all, the limit of the ratio of two functions. If we have a ratio, we have a fraction, and we have a combination of some of these functions, they're going to grow at different rates. And what these are set up for is if f grows faster. Okay, and we're going to be able to tell which one grows faster by this chart. Now, what I like to do is kind of look at, this and this. This is just the product of those two. Of course, if you take those two things and multiply them together, it's going to grow faster than that. But I think all the little C's and D's can confuse. So I'm going to look at this. This is an exponential, 2 to the x, 5 to the x. This is our friend factorial, which we will be visiting in a few weeks. So he grows faster than all those, and the fastest growing guy is this one. A power, basically a variable to a variable. And knowing this is going to help you in the more complicated limits that we're going to be dealing with, knowing that if the faster growing one is in the denominator, that the whole term is going to tend to 0. And if the faster growing one is in the numerator, the whole term will tend to infinity. So just something to keep in mind as you work through these limits, just to remind yourself about these rates of growth. Okay? All right.